Welcome to our comprehensive one-shot guide to inorganic chemistry for class 11 and 12. Inorganic chemistry is a branch of chemistry that deals with the properties and behavior of inorganic compounds. Unlike organic chemistry, which focuses on carbon-containing compounds, inorganic chemistry covers a vast range of elements and their compounds, including metals, nonmetals, and metalloids. In this video, we'll break down the key concepts, important chapters, and must-know facts to help you ace your exams. Let's embark on this journey, starting with the basics and building up to more advanced topics, ensuring you have a solid foundation for your studies. Periodic table is the backbone of inorganic chemistry. It organizes all known elements in a systematic way, highlighting their properties and relationships. Understanding the periodic table helps you predict element behavior, trends in atomic size, ionization energy, and electronegativity. Elements are arranged in periods and groups, with each group sharing similar chemical properties. The periodic table also distinguishes between metals, nonmetals, and metalloids, which is crucial for understanding their reactions. Mastering the periodic table will make learning inorganic chemistry much easier, so let's explore its structure and significance. Elements in the periodic table are classified into S, P, D, and F blocks based on their electronic configuration. The S block includes alkali and alkaline earth metals, known for their reactivity. The P block contains a diverse range of elements, including nonmetals, metalloids, and some metals. The D block, or transition metals, are known for forming colored compounds in variable oxidation states. Lastly, the F block consists of lanthanides and actinides, which are often placed separately at the bottom of the table. Understanding these classifications helps in predicting chemical behavior and reactivity. Periodic trends are patterns observed in the periodic table as you move across periods or down groups. Key trends include atomic radius, ionization energy, electron affinity, and electronegativity. For example, atomic radius decreases across a period and increases down a group, while ionization energy shows the opposite trend. These trends are essential for understanding why elements behave the way they do in chemical reactions. By recognizing these patterns, you can predict the properties of unknown elements and their compounds, making problem-solving much more straightforward. Chemical bonding is a fundamental concept in inorganic chemistry. It explains how atoms combine to form molecules and compounds. The main types of chemical bonds are ionic, covalent, and metallic. Ionic bonds occur between metals and nonmetals, involving the transfer of electrons. Covalent bonds involve the sharing of electrons between nonmetals, while metallic bonds are found in metals, where electrons are delocalized. Understanding these bonding types helps explain the structure, properties, and reactivity of various inorganic compounds. Ionic compounds are formed when metals transfer electrons to nonmetals, resulting in positively and negatively charged ions. These ions are held together by strong electrostatic forces, giving ionic compounds high melting and boiling points. Common examples include sodium chloride and magnesium oxide. Ionic compounds are usually soluble in water and conduct electricity when dissolved or molten. Understanding the formation and properties of ionic compounds is crucial for mastering inorganic chemistry, as many reactions involve these substances. Covalent compounds are formed when two nonmetals share electrons to achieve stability. These compounds can be simple molecules like water or complex structures like diamond. Covalent bonds can be single, double, or triple, depending on the number of shared electron pairs. Covalent compounds generally have lower melting and boiling points compared to ionic compounds and may not conduct electricity. Understanding the nature of covalent bonding helps explain the diversity of inorganic molecules and their properties. Metallic bonding occurs in metals, where atoms share a sea of delocalized electrons. This unique bonding gives metals their characteristic properties, such as electrical conductivity, malleability, and ductility. The strength of metallic bonds varies among different metals, influencing their melting points and hardness. Understanding metallic bonding is essential for explaining the behavior of metals and alloys, which play a significant role in inorganic chemistry and everyday life. Hydrogen is the simplest and most abundant element in the universe. In inorganic chemistry, hydrogen forms a variety of compounds, including hydrides, water, and hydrogen peroxide. Hydrides are classified as ionic, covalent, or metallic, depending on the elements involved. Hydrogen's unique properties make it essential in redox reactions and as a reducing agent. Understanding hydrogen chemistry lays the groundwork for studying acids, bases, and other important inorganic compounds. S-block elements include Group 1 alkali metals and Group 2 alkaline earth metals. These elements are highly reactive, especially with water and oxygen. Alkali metals like sodium and potassium are soft and have low melting points, while alkaline earth metals like magnesium and calcium are harder and less reactive. The chemistry of S-block elements is crucial for understanding their role in biological systems, industry, and everyday life. P-block elements cover groups 13 to 18 and include a wide range of elements such as boron, carbon, nitrogen, oxygen, and the noble gases. These elements exhibit diverse chemical and physical properties. The P-block contains metals, nonmetals, and metalloids, making it the most varied block in the periodic table. Understanding the trends and reactions of P-block elements is essential for mastering inorganic chemistry, as they form the basis of many important compounds. D-block elements, also known as transition metals, are found in the center of the periodic table. These elements are characterized by their ability to form colored compounds, variable oxidation states, and complex ions. Transition metals like iron, copper, and zinc are essential in biological systems and industrial processes. Their unique properties make them a key focus in inorganic chemistry, especially when studying coordination compounds and catalysis. F-block elements include the lanthanides and actinides, which are often displayed separately at the bottom of the periodic table. Lanthanides are known for their magnetic and phosphorescent properties, while actinides include radioactive elements like uranium and thorium. These elements are important in advanced technologies, such as nuclear energy and electronics. Understanding the chemistry of F-block elements is essential for students aiming to excel in inorganic chemistry. Oxidation and reduction, commonly referred to as redox reactions, are fundamental in inorganic chemistry. Oxidation involves the loss of electrons, while reduction is the gain of electrons. These reactions are crucial in processes such as corrosion, energy production, and metabolism. Understanding how to identify and balance redox reactions is a key skill for students, as it forms the basis for many chemical processes and industrial applications. Acids, bases, and salts are central to inorganic chemistry. Acids release hydrogen ions in solution, bases release hydroxide ions, and salts are formed from the neutralization of acids and bases. The strength of acids and bases is measured by their dissociation in water. Understanding the properties, reactions, and uses of acids, bases, and salts is essential for solving a wide range of chemical problems and for practical applications in daily life. Hydrogen forms a variety of compounds, including hydrides, acids, and hydrogen halides. Hydrides can be ionic, covalent, or metallic, depending on the elements involved. Hydrogen halides such as hydrochloric acid are strong acids and play a significant role in industrial chemistry. Understanding the types and properties of hydrogen compounds helps in grasping their importance in both laboratory and real-world contexts. Alkali metals, found in Group 1 of the periodic table, include lithium, sodium, potassium, rubidium, cesium, and francium. These metals are highly reactive, especially with water, and are stored under oil to prevent reactions with air. Alkali metals form strong bases called alkalis when combined with water. Their unique properties and reactivity make them important in both laboratory and industrial settings. Group 2 elements known as alkaline earth metals include beryllium, magnesium, calcium, strontium, barium, and radium. These metals are less reactive than alkali metals but still react with water and acids. They are important for biological functions such as calcium in bones and have various industrial applications. Understanding their properties and reactions is key for mastering S-block chemistry. Boron family, or Group 13, includes boron, aluminum, gallium, indium, and thallium. Boron is a metalloid while the others are metals. This group shows a mix of properties, with boron being used in glass and ceramics and aluminum being widely used in packaging and construction. Understanding the chemistry of Group 13 elements helps explain their diverse applications and reactivity. Group 14, the carbon family, consists of carbon, silicon, germanium, tin, and lead. Carbon is the basis of organic chemistry, but its inorganic forms like graphite and diamond are also important. Silicon is essential in electronics, while tin and lead have industrial uses. The chemistry of Group 14 elements is diverse, covering a range of oxidation states and compound types. Nitrogen family, or Group 15, includes nitrogen, phosphorus, arsenic, antimony, and bismuth. Nitrogen is vital for life, forming the basis of proteins and nucleic acids. Phosphorus is essential for energy transfer in cells. The chemistry of Group 15 elements involves a variety of oxidation states and compounds, making them important in both biological and industrial contexts. Group 16 elements, known as the oxygen family or chalcogens, include oxygen, sulfur, selenium, tellurium, and polonium. Oxygen is essential for respiration, while sulfur is important in industry and biology. These elements form a wide range of compounds, including oxides and sulfides, and exhibit interesting trends in reactivity and properties across the group. Halogens found in Group 17 include fluorine, chlorine, bromine, iodine, and astatine. These elements are highly reactive nonmetals and form salts when combined with metals. Halogens are used in disinfectants, medicines, and lighting. Their chemistry is characterized by strong oxidizing properties and the ability to form a wide range of compounds. Noble gases in Group 18 include helium, neon, argon, krypton, xenon, and radon. These elements are known for their lack of reactivity due to their full valence electron shells. Noble gases are used in lighting, welding, and as inert environments for chemical reactions. Their unique properties make them important in both scientific research and industry. Transition metals found in the D block have unique properties such as variable oxidation states, colored compounds, and catalytic activity. These metals are essential in industrial processes, including the production of steel and the catalysis of chemical reactions. Understanding the properties of transition metals is key for mastering advanced inorganic chemistry topics. Coordination compounds consist of a central metal atom or ion surrounded by ligands. These compounds are important in biological systems such as hemoglobin and in industrial catalysis. The study of coordination chemistry involves understanding the types of ligands, coordination number, and the geometry of complexes. Mastery of this topic is essential for higher-level inorganic chemistry. Crystal field theory explains the electronic structure and color of coordination compounds. It describes how the arrangement of ligands around a central metal ion affects the energy levels of d-orbitals, leading to the splitting of these orbitals. This theory helps explain the magnetic and optical properties of transition metal complexes, which are important in both chemistry and material science. Lanthanides and actinides, the F-block elements, have unique properties such as high magnetic susceptibility and radioactivity. Lanthanides are used in magnets, lasers, and phosphors, while actinides are important in nuclear energy. Understanding their electronic configuration and reactivity is essential for advanced studies in inorganic chemistry. Extraction of metals from their ores is a key topic in inorganic chemistry. This process involves steps like concentration, reduction, and refining. Different metals require different extraction methods, such as electrolytic reduction for aluminum and blast furnace for iron. Understanding these processes is important for both academic and industrial applications. Environmental chemistry focuses on the chemical processes occurring in the environment, including pollution, water treatment, and the impact of chemicals on ecosystems. Inorganic compounds play a significant role in environmental issues, such as acid rain and heavy metal contamination. Understanding these topics is crucial for addressing real-world environmental challenges. Inorganic chemistry has numerous industrial applications, from the production of fertilizers and glass to the manufacturing of metals and chemicals. Processes like the Haber process for ammonia synthesis and the extraction of metals are central to modern industry. Understanding these applications helps connect theoretical knowledge to practical uses in the real world. Qualitative analysis in inorganic chemistry involves identifying the presence of specific ions or elements in a sample. Techniques include flame tests, precipitation reactions, and color changes. Mastery of qualitative analysis is essential for laboratory work and for understanding the composition of unknown substances. Quantitative analysis determines the amount or concentration of a substance in a sample. Techniques such as titration, gravimetric analysis, and spectroscopy are commonly used. These methods are vital for accurate measurements in research, industry, and quality control. Understanding quantitative analysis ensures precision in chemical experiments. Inorganic chemistry features a variety of important reactions, such as combination, decomposition, displacement, and redox reactions. Understanding the mechanisms and outcomes of these reactions is essential for solving problems and predicting product formation. Mastery of these reactions forms the backbone of inorganic chemistry problem-solving. Oxides are compounds formed by the reaction of elements with oxygen. They can be classified as acidic, basic, amphoteric, or neutral, depending on their chemical behavior. Understanding the types and properties of oxides is important for predicting reactions and for industrial applications such as metallurgy and environmental chemistry. Hydroxides are compounds containing the hydroxide ion O. They can be strong or weak bases depending on their solubility and dissociation in water. Hydroxides play a crucial role in acid-base chemistry and are widely used in industry, such as in the manufacture of soaps and detergents. Understanding their properties helps in predicting their behavior in chemical reactions. Salts are ionic compounds formed from the neutralization of acids and bases. They have a wide range of uses, from table salt in food to industrial chemicals. Salts can be classified based on their acid and base origins, such as normal, acidic, or basic salts. Understanding the properties and uses of salts is essential for both academic and practical chemistry. Interhalogen compounds are formed by the combination of two different halogens. These compounds often have higher reactivity than pure halogens and are used in chemical synthesis and industry. Understanding their structure, properties, and uses is important for advanced inorganic chemistry studies. Oxoacids are acids that contain oxygen, hydrogen, and another element, usually a nonmetal. Examples include sulfuric acid and nitric acid. These acids are important in industry and laboratory chemistry. Understanding their structure, strength, and reactions is essential for mastering inorganic acid-base chemistry. Hydrogen peroxide is a common inorganic compound with the formula H2O2. It acts as a strong oxidizing agent and is used in bleaching, disinfection, and as a propellant. Understanding its preparation, properties, and decomposition reactions is important for both academic and practical chemistry. Ammonia is a key inorganic compound with the formula NH3. It is widely used in fertilizers, cleaning agents, and as a refrigerant. Ammonia forms a variety of compounds, including ammonium salts. Understanding its preparation, properties, and reactions is essential for both academic studies and industrial applications. Phosphorus forms a range of important compounds, including phosphoric acids and phosphates. These compounds are essential in agriculture, industry, and biological systems. Understanding the structure, properties, and uses of phosphorus compounds is key for mastering inorganic chemistry topics related to group 15 elements. Sulfur forms a variety of compounds, including sulfur dioxide, sulfuric acid, and sulfides. These compounds are important in industry, environmental chemistry, and biological systems. Understanding the preparation, properties, and uses of sulfur compounds is essential for both academic and practical chemistry. Chlorine is a highly reactive halogen used in water treatment, disinfectants, and the production of PVC. Its compounds, such as hydrochloric acid and bleaching powder, are important in both industry and laboratory chemistry. Understanding the properties and reactions of chlorine and its compounds is crucial for mastering halogen chemistry. We've covered the essential topics of inorganic chemistry for Class 11 and 12 in this one-shot guide. From the periodic table and chemical bonding to the properties of elements and their compounds, you now have a solid foundation. Remember to focus on understanding concepts, practicing problems, and connecting theory to real-world applications. With consistent effort and a clear grasp of these topics, you'll be well prepared for your exams. Good luck with your study.